Hello class, this is section 6.5, trigonometric form of a complex number. The complex plane. Plotting a complex number z equals a plus bi in the complex plane is the same as plotting the point a comma b in the rectangular coordinate system. In the complex plane, the horizontal axis is called the real axis and the vertical axis is called the imaginary axis. Let's take a look. As we see the typical x and y axis take shape, if we were to go ahead and rename the x-axis now the real, and the y-axis the imaginary, we have the complex plane. So let's take a look at an example ordered pair. And of course we're going to use a plus bi again, as we all remember from back in pre-calc. Let's start with the following complex number, 3 plus 2i. And notice how I've identified a as 3 and b as 2. So as far as plotting this particular imaginary number on the complex plane, we're going to identify it as 3 comma 2. So pretty simply, 3 units to the right, 2 units up, and there you have it, 3 comma 2. The absolute value of a complex number z equals a plus bi is the distance between 0 comma 0 and a comma b. Hence, the absolute value of z is equal to the absolute value of a plus bi, which is equal to the square root of a squared plus b squared. This may look familiar to you guys. For example, let's reflect back and try to think about this formula. So if we were to solve for c, we can easily take the square root of both sides. And in turn, in this equation, we're really solving for z. So let's take a look at example 1. Find the absolute value of z, which is equal to 4 minus 3i. So pretty simply, let's first identify 4 minus 3i as it would look as an ordered pair. 4 comma negative 3. So that's your a, that's your b. So the absolute value of z is equal to the square root of 4 squared plus, and I'll put negative 3 in parentheses, negative 3 squared, which of course we can say is what, 16 plus 9, or square root of 25, and then of course 5. So that's our end result. What about graphically speaking though? Let's draw ourselves an xy axis or real imaginary at this point, of course. So if we're looking at the ordered pair 4, negative 3, 4, negative 3 is in the fourth quadrant. The starting point, 0, 0, to that ordered pair 4, negative 3 takes shape like this. We can identify z in particular now as 5. And we can actually create, as we're more than well aware, a right triangle from this. Okay, so all of our trig principles can apply now. Looking at our right triangle in the fourth quadrant, hypotenuse 5, which again is formulated from our two legs of length 4 and really negative 3, being careful that we're going down in the fourth quadrant. Okay, moving on. Trigonometric form of a complex number. If theta is an angle in standard position, measured counterclockwise from the positive x-axis, with terminal side containing the point a comma b, then you can write the following. You can write a as r times cosine theta, and you can write b as r sine theta, where r is equal to the square root of a squared plus b squared. So this relationship pops up again. And in essence, it does in fact relate back to the Pythagorean theorem. Let's graph it. Okay, so we make ourselves an XY axis, or again, relatable real imaginary axis. And clean that up a little bit. Okay, so if we're going to go ahead and plot the ordered pair, let's say A comma B in the second quadrant. We don't know exactly what A and B are, but we do know that they are in the second quadrant. And if we're going to go ahead and involve theta here, we can say that theta is a second quadrant angle. In other words, theta is in between pi over 2 and, of course, pi. Let's bring back right triangle trig again, dropping down our altitude. We can, of course, say this is A. We can say that this is B. Okay, and then I'm going to go ahead and involve theta prime again. This little guy right here, technically, we're going to go ahead and identify as theta prime. So again, going all the way back to when we discussed reference angles, this angle in particular is in fact different than theta. Okay, so you do need to know what quadrant you're in. The trigonometric form of the complex number z equals a plus bi is z equals r cosine theta plus r sine theta I. Similarly then, if you were to factor out r, you actually are left with cosine theta plus I sine theta. And I say similarly, but these are actually equivalent expressions. This, of course, being A, this being B. Factoring out that common factor leaves us with this, where again A equals r cosine theta, B equals r sine theta, and r equals the square root of a squared plus b squared. And then we're going to talk about theta, of course, where the tangent of theta is equal to b over a. Remember, guys, opposite over adjacent, same concept. The number r is called the modulus of z, and theta is an argument of z. So some new terminology here for us to, let's sink in here. Let's move on to the next page and start talking about these things more in depth. So example 2. Write z equals -2 plus 2i in trigonometric form. Okay, so let's start off maybe by rewriting -2 plus 2i as an ordered pair, which hopefully is very comfortable for us. -2, comma 2, there's A, there's B. I think it's actually important for us to get a visual of this right away so we can start thinking, okay, what quadrant am I dealing with? What theta value am I dealing with from there? So -2, 2. Okay, so there you go. Pretty simple second quadrant angle. All right, so let's start thinking about using trig again, what theta happens to be. R, start with this, equals the square root of -2 squared plus 2 squared, which if we simplify, of course, -2 quantity squared is 4, plus 2 squared 4, 4 and 4 gives us 8, so square root of 8, and I'm going to simplify that to √2. Let's find theta. So going back to our fun trig ratio, tangent is opposite over adjacent. We're going to take the inverse tangent of opposite over adjacent. Speaking of which, let's look at our picture again here. Let's drop down our altitude. Again, I'm going to use the appropriate sign here for the adjacent side, -2, and the opposite side, +2. Okay? So opposite over adjacent. We can do the math on this actually pretty simply, thinking about our unit circle. Inverse tangent of -1, as we think about sine and cosine being equivalent but opposite of each other. And we can only, of course, think of an angle in the second quadrant or fourth quadrant that has this value. Since we know that it's in the second quadrant, we can immediately jump to 135 degrees. In other words, the tangent of 135 degrees is -1, as is this fourth quadrant angle, of course, that we know to be 315 degrees. I'm going to write this in radians as well, 3 pi over 4. Okay, so we have theta, we have r. And I do want to highlight, just so that we're accustomed to dealing with this angle again, theta prime. Theta prime is the reference angle, the difference between pi and 3 pi over 4. So pi over 4. That's an important angle, of course, if we're talking about doing right triangle trig, and particularly with reference angles being between 0 and 90 degrees, or 0 and pi over 2. All right, let's go ahead and get the trig form completed here. Z now it will be equal to, so we have r, so it's 2 root 2, and then we've got theta. I'm going to go ahead and write my final value for theta using radians, so cosine of 3 pi over 4 plus I sine 3 pi over 4. And yes, you could use degrees, but typically speaking, we start looking at this type of trig form in radians. And we'll go back and forth between radians and degrees, but that's a good final answer. Example 3. Write 4 times the quantity cosine 5 pi over 6 plus I sine 5 pi over 6 in a plus bi form. Okay. So in a matter of speaking, we're going in the opposite direction. Okay, if you think about what we did in the last example, we came up with z given a plus bi. Now we're given z and we're going in a plus bi form. Okay, so let's get the ball rolling with starting with our form here, z equals. Okay, so we are going to identify, we're going to have to identify r and theta. So let's go ahead and take the cosine of 5 pi over 6 and the sine of 5 pi over 6. Think of your unit circle, right? The cosine of 5 pi over 6, negative root 3 over 2. The sine of 5 pi over 6, 1/2. So we can actually rewrite our expression now, if you think about it, as 4 times the quantity, negative root 3 over 2, plus I times 1/2. Okay, simply now just distribute the 4, or just take 4 divided by 2, easy enough, so negative 2 radical 3, and then distribute it to this term, and you get plus 2i. Ladies and gentlemen, that is your final answer. This is your A, this is your B. So A plus BI form is what we see. Now let's check. Let's check to see that our work paid off. Okay, and in order to do this, we can think about literally the ordered pair now, negative 2 radical 3, comma 2. And then reflect back at the very beginning of our lesson when we looked at the real and imaginary axis. All right, so negative 2 root 3. Okay, if we were to do a quick number crunch on this, let's see, negative 2 square root 3. In other words, in decimal form, we've got negative 3.46. Okay, and then of course comma 2. So negative 3.46 comma 2 puts us roughly, I don't know, let's say about here. Okay, so this, therefore, whoops, this would therefore be our appropriate z value. When I say appropriate z value, let me highlight this. Okay, and r value for that matter. Z and r are one and the same. This is 4. Okay, our theta value right here, well, we knew that from the get-go. That was 5 pi over 6. Okay, So we are looking at a second quadrant angle.